So in the previous lectures, what we have studied is the basic building block of a sequential system. It's a flip-flop, and we have studied how the sequential system or sequential circuit is different from a combinational logic circuit. Then we studied two very fundamental building blocks of sequential circuit model, that is a resistor and a counter. Okay. Now we are in a position to study the sequential circuit model and types thereof, and we'll also discuss about the standard forms of describing the sequential circuit model. One of the form is very known to you, that is you can describe them with the help of truth table, or you have studied the excitation table representation. In this lecture, we'll also learn about two new representations, that is state table and state diagram. Before moving on to that, let us first see the types of sequential circuit model and the differences between them. To start with, let us see a sequential circuit model given over this. So this is a very general sequential circuit model. What is the feature of the sequential circuit model? See, if we look at the different blocks, this is a combinational logic block, and it's called a next state decoder. What is the function of this next state decoder? It accepts the input, say at time t, and the feedback from memory elements. What are the memory elements? We have seen that these memory elements are the fundamental elements that differentiate a sequential circuit from a combinational logic circuit. This memory element basically stores the present state, that is at time t. Right? So this information is then fed back. This is a kind of feedback. This information is kind of feedback to the next state decoder. A next state decoder, depending upon this present state and the input values, will generate a signal that is nothing but the next state variable. And this variable will be the variable that will be stored in the memory element, and this will become the present state for the time t plus 1. That is, in the next state, it will become the present state. It's a recursive process. So this next state variable is basically a function of the input variable at time t and the present state at time t. And this next state variable is actually the memory elements at time t plus 1. And this will again be updated. Now at t plus 1 instant, what will happen? This sequence of operation will again continue. New input values will come. This new input values, along with this present state at t plus 1, will be used by this next state decoder to generate the next state that will be stored in the memory element, and that will be the value of the memory element at t plus 2, and this will then be called the present state at t plus 2. So in this way, in a recursive manner, the next state decoder will generate the next state depending upon the present state, which is stored in the memory element, and the input at the present moment or the present state. And this next state decoder output, this is called the next state variable, will be stored in the memory element, replacing the previous values. So the present state for t plus 1 instant will be updated. At each of these instants, whenever there is a transition taking place, the output decoder, on the other hand, which is again a combination logic circuit, will generate the output as soon as there is a change in input. And this output will be a function of the input variables and the present state variables. So these output variables will be updated at t depending upon the present state and the input variable. Similarly, at t plus 1, this will be updated by input at t plus 1 along with the present state at t plus 1. Right? So in this way, a sequential circuit will operate, and it will generate the next state and the output. Mind it, the output is generated as soon as there is a change in input, But the next state will appear as a present state only after a clock transition has taken place. That is, if it's a sequential, synchronous sequential circuit, it will be triggered by a clock. So only the memory element will be updated to a new value at the clock transition. So the t plus 1 will be updated. The present state of t plus 1 will be updated by the next state at t, calculated at t. So this is a recursive process that will continue, right? So this is a very fundamental sequential circuit model that we have discussed. And this sequential circuit models can be classified in 5 different categories, right? So they are normally classified as class A, class B, class C, class D, and class E, right? So there are 5 different models for sequential circuit. So this model is basically a class A model. So what is the feature of this class A model? The main feature of this class A model is that this output decoder, they generate the output based on the present state and the input signal. Okay, typically this sort of sequential circuit where the output depends on the present state and the input at the present instant are called millicircuits or millimodels. It's based on the name of a famous mathematician G.H. Milli. So this sort of sequential circuit models are called millicircuits or millimodels, right? Or sometimes you call them as milli machine, right? The feature of this milli machine is that the output at any instant is a function of present input and the input. So the thing is that this is to be noted that this is at instant t, this is at instant t, and whatever output you are getting is also at instant t, right? So this is the feature of a milli machine. Now, obviously, there will be class B, C, D, E, other sequential circuits as well. So let us look at them. I'll go through them very briefly because they're only very trivial things. I'll zoom a bit so that you can see. Let us concentrate on circuit B and C. So if you see this model, in this case, what is happening? The output decoder is generating output based only on the present states. The output doesn't depend on the inputs at any instant. Similarly, in this case also, in class C model, if you see, the output decoder is developing output. There is no output decoder actually. The output is nothing but your present state, right? So in this case, since the output is independent of the input at any instant, this class B and C type of sequential circuits are named after EF mode as Moore machine. So what is the basic difference between a milli machine and a Moore machine? In a Moore machine, the output is only the function of the present state, whereas in the milli machine, the output is function of the present state and input. So it's a combination of present state and input. But in a Moore machine, the output is only a function of present state. Now, in the first case, in the class B, you can see the output may directly is not directly the present state. There may be some output decoder logic, which is nothing but a set of combinational logic gates or circuit, which will decode this present state to generate the output following some Boolean expressions. So this is for the class B. Whereas in class C, the output is directly given by the present state. Okay, there's slight there's a mistake in this printing. I just correct it. This signals will not come from this path because this signal is your next state, and this next state decoder generates the output. There is the next state based on the input and the present state. So this actually could come from, sorry, you make this correction, huh? Whenever I put you this, you make this correction. And this will not be there. This is a very so the output, which is nothing but the present state, will be fed back to the next state decoder, and the next state decoder, depending upon the present state and the input, will generate the next state variables, which will again be stored in the memory element, and this next state variables will become the present state for t plus 1th instant or the next instant, right? So these are the two mood models. Okay. Now there will be class D and class E circuits. What are these? In class D circuit, the basic feature is that, see, the inputs are there. The next port decoder or next state decoder will generate the next state depending upon the input signals only. There is no feedback involved. And this memory element, it will be stored in the memory element. And the output at any instant is nothing but the present state at that instant. Okay. So depending upon the input at t, it will generate t plus 1 ns at t, but this ns at t is nothing but your present state at t plus 1, and this output will be pst. So second output will be pst plus 1, and this way this sequence of operation will tend to continue. The only difference is that there is no feeding back of the present state to the next state decoder. The next state decoder generates next state based on the input only. There will be Boolean expressions for that. And the last classification is a class E circuit, where typically it only has a memory element. Okay, so whatever input comes, it is stored in the memory element, and that input itself becomes the present state and output. So it's a simply memory element or storage element. Right? So if you go by the nature of the circuit, if you go from E to D, obviously D will be more complex, C will be more complex since it involves a feedback, B will be even more complex because it has this output decoder, and similarly A will be much more complex or equivalent to class B. So in this order, starting from E, D, C, B, we will have more and more, I don't know, should not say complex, but involved circuits or sequential circuit models, right? So these are the classifications of general sequential circuit models. Now what we'll study is how to analyze these sequential circuits, right? Now the sequential circuit can be analyzed using what we've already learned, that it can be analyzed using standard truth tables. Now for sequential systems, these truth tables are normally termed as state tables. Okay, so it can be termed as state tables, and corresponding diagram in the pictorial representation, it will be called a state diagram. Okay, now the behavior of the sequential circuit will be determined from the input, output, and the present state of the circuit, right? So the output and the next state, as we've already seen, are the function of present state and input. Sometimes the input may not be there, sometimes the present state may not be there, but in general, they're function of input and present state or present state only, or inputs only. Okay, the analysis of the sequential circuit therefore will consist of obtaining a suitable description that should demonstrate the time sequence of input, output, and state. Right? Now the question is that this sort of descriptions we've already seen in case of a flip-flops or in case of a register, counter. But how do you classify a particular system to be a sequential system or a synchronous sequential circuit? Now that can be classified if the following statement is verified. That is, a logic diagram is recognized as a synchronous sequential circuit if it includes flip-flop with clock input driven directly or indirectly by a clock signal. Since it's a synchronous one, it should include a clock signal that is being driven directly or indirectly. And the most important part is that direct set and resets are unused during the normal functioning of the circuit. Okay. We have seen that in asynchronous sequential circuit, there is a provision of, there's not provision, the set and resets are used, asynchronously. But in a sequential circuit, if it's a synchronous one, we'll expect the set and reset operation to be unused during the normal functioning of the circuit. Does that mean in a sequential circuit which is synchronous, there won't be any set or direct set or reset? Obviously, there will be direct set and reset, but that operations will be periodic. That is, that operations will take place only after a set of predefined operations have taken place, and then the direct set and reset, whichever is applicable, will take place to reset or to preset the entire logic circuit. But any intermittent set or reset operation should not happen. If a logic diagram satisfies this, that it is driven by a clock, either directly or indirectly, and the direct set and resets are unused during normal functioning of the circuit, then it will be called a synchronous sequential circuit. So it may involve different types of flip-flop, and it will also involve a set of combinational gates or a circuit consisting of combinational gate. The output of this combinational gate will be used to drive the flip-flop. So therefore, the Boolean expression that or the Boolean function that describes the operation of this combinational gate or the combination or the arrangement of the combinational gate, the output of which drives the corresponding flip-flops, will be called the flip-flop input equations. Now we'll to discuss or to analyze the sequential circuit. We should start with first the flip-flop input equations, or how or in which manner the flip-flops are excited. So before going to that, we have to adopt to some convention. So what is the convention of denoting the dependent variable? The dependent variable in the flip-flop input equation by the flip-flop input signal. So if the flip-flop is a D-type flip-flop, that is, the input is denoted by D. Since we know for D-type flip-flop, the input is denoted by D, and there are, say, two flip-flops, A and B. So the input to the A flip-flop will be denoted as DA, and input to the B flip-flop will be denoted as DB. So this D will indicate that the D flip-flop is used, and this A will indicate this is the flip-flop in position A. Similarly, if a T flip-flop is used, then we'll have TA and TB. This is the flip-flop input equations, and we shall derive the expression for DA, DB or TA, TB in terms of various other circuit parameters like inputs and other things, inputs and present states. Right? Let us see how to derive the flip-flop input equation given a particular sequential circuit. Sorry. So this is the example of a sequential circuit. Okay. Now where X is the input and Y is an output. And what we have done, we have used two D flip-flops. So this is your D flip-flop A, and this is your D flip-flop B. So that the output is marked as A and A bar, and this is B and B bar. Let us see how this AND gates and this OR gates are used. If you consider the first AND gate, this is the input, right? And this is output, Y. So if you consider this AND gate, what is that signal? This is X, and this signal is A. So this signal is AX. This is again X, and this is your, see, B from this side. So this signal is BX. So what is DA then? AX. So this is the input equation for flip-flop A. Right? Similarly, if you consider this AND gate, this signal is A bar, and the signal is X. So what is your DB? A bar X. So this is the input equation for flip-flop B. So what is the output equation now? If this is the output equation, see, this signal is your B and this signal is your A. So it is A plus B. This is X. So this will be X bar. So Y will be A plus B X bar. So this is your output equation. So these are the driving equations for this sequential circuit model. Understood? DA, the input equation for flip-flop A is AX plus BX, DB equal to A bar X, and Y equal to A plus B X bar. I request you to just note down these three equations. Okay, you just note down these three equations because in the next state, what you will do, will develop the corresponding state table for this. Okay, if possible, what you do, I'll just write down the equations. Input equation dA is equal to AX plus BX, dB equal to A conjugate X, output equation Y equal to A plus B. You either take a screenshot of this or take a note of these equations. Better to take a screenshot of this because we will be discussing the state table or state diagram for this. Okay, all of you take a screenshot for this. Okay, and keep it in your mobile or laptop screen so that whenever I ask you, you can refer back to them. Okay, done?
Yes, sir.
Okay, so now what we'll study is state table, how to generate the state table corresponding to this. Now, the state table, hello? Yes? Okay. The state table, what it does, it represents the functional relationship between the input, output, and the flip-flop states for a sequential circuit, right? Now, the state table for sequential circuit will therefore constitute this different columns. The present state, since there are two flip-flops, A and B, then the input, then the next state, that is at t plus 1, present state at t, input at t, the next state at t plus 1, and output. So we should depict this four columns. Okay, and since there are two flip-flops, so there will be two entries in present state and next state. And since there is a one output, so there will be a single entry in the output column, right? So the representation is done in such a manner that first this present state is written down in such a manner. See the combinations, the possible combinations are 0, 0, 0, 1, 1, 0, 1, 1. Now for each of these present state combination, the output or input may be 0 or 1. That's why they are repeated like this and put in a cluster. Similarly, this 0, 1 can have both the inputs 0 or 1, 1, 1, 1, 0 can both the inputs 0 and 1. In this way, they are clustered like this. The beauty is that if you look at this series now, it's nothing but 0, 1, 2, 3, 4, 5, 6, 7. Right? This is how this table is formulated. Right? From 0, 0, 0 to 1, 1, 1. The corresponding next states will now be developed based on the corresponding equations. Now, if I write down the corresponding equations, see, I'll just write dA here and dB here. So I'll just write the equation. What is dA? dA is nothing but AX plus bx, and db is nothing but a bar x. Now, in case of a d flip flop, we know that the output of a d flip flop at t plus 1th instant is nothing but d at t. So, this a and b, that is the t plus 1th instant output, will be nothing but same as d at t and db at t, right? Similarly, the output equation is given as y equal to a plus b x bar, right? Now let us check one by one. For a equal to 0, b equal to 0, and x equal to 0, what is dA? 0. What is dB? 0. So obviously a and b will be 0. And what about output? A and b are both 0, so it will be obviously 0. Now, for the next condition, a equal to 0, b equal to 0. So obviously dA will be 0, right? And dB, a bar x, since x equal to 1, but a bar is 1, so it will be 1. That's why this will be 1. What about output? See, x bar is 0, so output will be obviously 0. So in this way, for 0, 1, we will get dA to be 0 and dB to be 0. But in this case, see, a plus b equal to 1, x bar equal to 1, so output will be 1. In this way, you can generate the state table corresponding to this particular sequential circuit model. বোঝা গেল জিনিসটা কি হচ্ছে? আচ্ছা, যদি মনে করে আমি লিখে দিতে পারি একটা ইকুয়েশন, তাহলে বুঝতে পারবে। দ্যাট ইজ a t plus 1 is nothing but dA at t, and b t plus 1 is nothing but dB at t. So following this, you can generate this state table, right? Now, let us discuss about the features of this state table. In general, if a sequential circuit has m number of flip-flops, okay, and n number of inputs, then how many rows will be there? Since for each flip-flop, we'll have two output conditions, two present state conditions, right? And for each input, there are that n number of situations. So total number of rows will be this will be the number of rows in a state table. That is, total number of state or the binary numbers that you will go through will be, let me clear this out, 2 into m plus n. So total number of rows, in this case, what is your m? 2, n equal to 1, right? So I don't think 2 to the power, there should be 2 to the power. So what will be the cap? 2 cube, right? So there will be 8 number of rows corresponding to this case. M equal to 2, 2 number of flip-flops and 1 input. And so it will go through the states 0 to 2 to the power 3 minus 1, right? Now, this sort of a state table is called a one-dimensional state table. Why? Because in this case, we have written down all the possible input situations corresponding to a particular present state, considering a single column feature. That is, the possible combinations of input given a present state 0 0 is given as 0 0 0 and 0 0 1. So it's written in one dimension. So what we could have done, we could have put the present state 0 0, and instead of a single input, we could have incorporated two inputs. That is one case, two cases of inputs, x equal to 0 and x equal to 1, and corresponding to each of them, we could have derived our next state and output. Now, if I show you the table, it will be much more easier to apprehend. And then this table will be called a two-dimensional state table. See what is done? The present state is there. Since there are two flip-flops, there are only four combinations: 1, 2, 3, 4. Now for each of this combination, you can have an input x equal to 0 or an input x equal to 1. If the input is x equal to 0, then the possible next states of AB are listed in this section. And if x equal to 1, then the corresponding next state values of A and B is written in this. Similarly, if someone is trying to join, similarly for this output case, x equal to 1, the output equation, the output relation is given by this column, and for x equal to 0, corresponding output is given by this. So this is called a two-dimensional state table. Now, what is the difference between a one-dimensional state table and a two-dimensional state table? First of all, in two-dimensional state table, it is very concise, and it is obviously applicable only, or more applicable only, when the output depends on the input. That is in case of a millimodel. Because in those cases, if there are n number of outputs, it will constitute 2 to the power n number of rows. To reduce the number of rows, or to reduce the length of the table, instead of going for a long table, we are going for a flat table or a fat table. So it will be easier for anyone to read that particular table rather than a one-dimensional table, right? And they can clearly see what are the possible situations that one may arrive. So this is obviously not very useful for mood model, but the next state or the output is function of present state only, and there is no function of input in case of output. But obviously the transition from present state to next state will also be very simply put in a concise manner. Okay, that's why the two-dimensional state tables are much more widely used. So just to give you a hint how to read this table, suppose your present input is 0 0. If for that your present state is 0 0, sorry, if your input corresponding to that state is 0, then the corresponding next state will be 0 0, and the output will be 0. On the other hand, if corresponding to the present state 0 0, your input is 1, then the corresponding next state will be 0 1, and the output will be 0. This follows from the input and output equation, because see, in output equation we had x bar. So whenever this x is 1, this ideally will be equal to 0 for all x equal to 1. So this column will all be 0. Okay, but in this column, x bar will be 1, but depending upon the value of a plus a and b, it will be either 0 or 1. This is how a two-dimensional state table can be read. Now, this particular circuit that you have considered is typically a millimodel, because the output is a function of not only the present state but also the input. See, it's a function of a plus b, the present state, and the input. So let us consider then a example of a mood model where the output is directly the function of present state only. See how it will be. This is basically, sorry, the circuit. Now, see, in this case, DA, this is your DA, is defined as X and Y are there. So this output is X XOR Y. And this output is A. So this output is A XOR X XOR Y. So this is your input equation. That's it. Input equation, and the output is nothing but A. So this is your output equation. So given this circuit, if you want to write down the corresponding state table, how it will look like? This is the corresponding state table. How it can be explained? Say since there is only one flip-flop, so there will be present state will constitute only one term, A, and there will be different combinations of input. There are two inputs. So for any initial state or present state A equal to 0, there will be only two cases of present state, A equal to 0 or A equal to 1. So for A equal to 0, there may be four different combinations of input, that is namely 0 0, 0 1, 1 0, and 1 1. Right? Corresponding to this, what would be the value of dA, which is defined by this expression? Because we know the expression that A of t plus 1 is the next state is given by dA at t, and that is nothing but A at t XOR X at t XOR Y at t. Right? So now we just follow this table, how it can be concluded. For A equal to 0, first this XOR gate will operate. For X equal to 0, Y equal to 0, this will be 0. Now A is again equal to 0, so this will be 0. So dA, whatever dA, it will be 0. So A t plus 1, this is obviously t plus 1, this is t, this is t, this is t. So A t plus 1 will be also 0. In the second case, when X equal to 0, Y equal to 1, so what about this? This will be 1. This is 0, this is 1, so this will be 1. So dA will be 1. So what about A t plus 1? It will be 1. But in all the cases, what is Z? Z is nothing but the output equation A. So since A is all 0, so output will always be following that. See, the output is only the function of the present state. That is why it's called a Moore model. So if you continue like this, see in this case also, X equal to 1, Y equal to 0. So output of the first XOR gate will be 1. Again 0, so it will be 1. So 1. 1 1 XY, first XOR gate output will be 0. 0 0, it's a 0. It will be 0. Things like that. When this is 1, and if you go through the same combination of inputs from 0 0 to 0 1 1 0 1 1, you'll get another set of dA, and corresponding to that, you'll get the next state given by this. Again, note that the output will exactly be same as the state, the present state at t, right? So this is how a state table for a Moore model circuit would look like, and how to derive that state table for a Moore model circuit. Okay, in this preliminary lectures, we will be discussing about the analysis of sequential circuit. This state table will be very helpful in designing a sequential circuit, because we've already seen how the excitation table can be used in interconversion of flip-flops or deriving a logic circuit, like we have derived a counter, mod counter in the last class using that excitation table. Now the next important representation is a state diagram, which is nothing but a graphical representation that it constitutes the same information, or it conveys the same information as does a state table, but only in a pictorial manner. So it has certain advantages and certain limitations, but the advantages are much more. See, because any pictorial representation will aid the designer or the system engineer to quickly relate the operations that are actually taking place. So let us see how a state diagram looks like. This is a typical state diagram. This within the circle are the states of the system, and this for different types of models, these lines indicate the state transition. So these circles, they represent states, and these lines, they indicate state transition. Obviously, they are directed lines. Okay, if it starts from a particular state and returns back to the state, then it's called that. It means that if these conditions are satisfied, then the state doesn't change. And this again means if these conditions are satisfied, then state moves from this state to this state. Obviously, these two corresponds respectively to a milli and a mole model. Let us first start with the milli model, which is nothing but this is a state diagram corresponding to the first circuit that we have drawn. Okay, now I think I shall draw the state diagram starting from the scratch. Enough. Let us see. Is this table still visible? দেখা যাচ্ছে তো? ঠিক আছে? So
Yes, sir.
let me see if I can copy this thing. No, I don't have any option of pasting that particular document. Let's just check. Do I have a paste option? Yes. And to move this one. So how to move this one? I think we should be using this. Okay, this table is visible.
Yes, sir, it is visible.
Now let us try and draw the state diagram that corresponds to this particular state table. This is state table. Now what are the possible states that we have? We have a state 0, 0. So marked like this. Then we'll have 0, 1, marked like this. Then we'll have 1, 1, marked like this. Then we'll have 1, 0. So it should be marked in this sequence. If you move from clockwise, it should be 0, 0, 0, 1, then 1, 1, then 1, 0. Okay. So let us see if the present state is now 0, 0. And if you produce an input x equal to 0, then what is the next state? It remains at 0, 0. And what is the corresponding output for x equal to 0? The corresponding output is also 0. So this is represented by a line like this, where it will have two indices, that is 0 is the input, followed by slash, followed by another 0, that is output. So if I mark this input divided by output, note that this input is at time t and output as time t. So it depicts that if at time t the system is at state 0, 0 and the input is 0, then the corresponding output will be 0 and there will be no state transition taking place. Right? Next, suppose the input is now changed to x equal to 1. So what will be the next state? 0, 1. What will be the output? It remains 0. So it is depicted by this arrow, where the input is 1, this, and the output remains 0. So it means that at t, the state is 0, 0. Now, if at time t, if you give an input 1, the output will remain at 0. But as soon as the next clock arrives, the state will move from 0, 0 to 0, 1. That is a state transition will take place from 0, 0 to 0, 1. Right? Now what happens? See, at any state 0, 0, 0, 1, 1, 0, 1, 1, there will be only two possible cases of input, 0 or 1. So there will be exactly two arrows or the directed lines that will be emanating from each of such states, right? Indicating the state transition if that particular input is applied, with the corresponding output being also represented followed by a slash, right? So now it has moved to state 0, 1. If your input is 0, then what will be the corresponding output? 0, 0. Sorry, corresponding next state 0, 0, and the corresponding output is 1. So if the input is 0, it will come back to state 0, 0, and the output will be 1. So what does that mean? If it is at state 0, 1, and if you change the input to 0, then the corresponding output will be 1. And as soon as the next clock trigger arrives, the state will change over from 0, 1 to 0, 0. So there is a transition of state taking place. Similarly, if the input is now 1, when it is at state 0, 1, what will happen? It will move over to the next state 1, 1. Or what will be the corresponding output? 0. So for 1 input, it will move over from 0, 1 to 1, 1, and the corresponding output will be 0. One thing you should keep in mind, that input is at time t and the output is at time 0, at time t, sorry, and the transition will only take place at t plus 1 when the next clock has appeared. So this green arrow indicates the transition, and this 1, 0 indicates the actual input and output condition when it is at 0, 1. Okay? Now it has moved on to the state 1, 0. Sorry, not 1, 0, actually 1, 1. Again, two cases will appear. If x equal to 0, then it will move to state 0, 0. This if 0 input is applied, and the corresponding output will be 1. So what is the input? 0. What is the output? 1. Understood? And if we apply input 1, then what will be the next state? 1, 0, and the output will be 0. Right? So the state has now moved on to 1, 0. So there will be again two input conditions. For 0, it will move to 0, 0. If we apply input 0, what will be the corresponding output? Output will be 1. And at the next clock pulse, it will move over to 0. So the transition will be something like this: 0, 1. If we apply input 1, then it will produce an output 0. But the next state is 1, 0. So this is the complete state diagram corresponding to this milli-module circuit. Now, সবাই বুঝতে পেরেছো? কারো ডাউট থাকলে বলো।
No, sir.
Okay, fine. Okay, next, let us consider the Moore model circuit. So given this circuit, let us try and develop the corresponding state diagram. So this is a state table corresponding to a Moore circuit. Right? Now in this case, there is only one flip-flop. So the number of states will be 2, either at state 0 or at state 1. Right? Now, again, the transition from state 0 to state 1 doesn't depend on the input. Sorry. Yeah. The transition from 0 to 1 depends on input, but the output is independent of the input. See? The output, because the output equation was Z equal to A. So what should we do? We should not bother much about the transition from present state to next state, because the output is always same as the present state. So that can be included in the description of the state itself, because 0 is the present state and that too is the output. 1 is the present state and that too is the output. So if we follow the notation, just like present state followed by output, that is within the state diagram. Now the state transition from a present state to the next state will be a function of input, right? Now if we see the table where there is no transition taking place, if I note down those values, so those will be like this case, it will remain at state 0. Suppose it is at state 0 to start with. In this case, there is no transition. So corresponding to this combination of input, that is xy equal to 0, 0 or xy equal to 1, 1, there will be no state transition taking place if it is at state 0. So this will be marked like this. Since these are two different conditions or combinations of input, they are separated by a comma. Now, if it is a state 0, see the table, if it is a state 0, then the state transition from 0 to 1 takes place for the combination xy 0, 1 and xy 1, 0. So this transition will take place 0, 1 and 1, 0. If you look at clearly here, if both the inputs are same, then there is no state transition taking place. But if both the inputs are complement to each other or different, then only the state changes from 0 to 1. Right? Again, it should be noted that suppose it is at state 0 with output 0, so given input sequence 0, 1. So output will remain 0. Only when the next clock appears, the state will change from 0 to 1, and correspondingly, the output will now get changed from 0 to 1. Now it is at state 1, 1. See? So if it is a state 1, 1, let us see where it doesn't change its states. When the input is 0, 0, it doesn't change its state, and when it is input is 1, 1. So clearly, these will be the two input conditions for which it remains in the same state. And then when it does change the state, when they're like 1, 0 and 0, 1. So this is the complete state diagram following this mood model. Now understood? ঠিক আছে? Now, based on the previous concept or the concept of this state diagram for a milli model, should not mention that, we shall develop the concept of what is called an equivalent state. Now, how that's going to develop? For that, let us copy a particular portion. Just a minute. I'll not take the burden of drawing this again, so I'll just copy this. I'll paste it here. I guess it's visible. So now this is the state diagram corresponding to the milli-modal circuit that we have discussed. Now let us explore the concept of equivalent state. What is the equivalent state? The equivalent state concept is used to reduce the number of states in a state diagram. How the two states are said to be equivalent if the responses for each possible input sequence is an identical output sequence. That is, response to each. I should not write this. I'll show the definition on the PDF itself. Just a minute. Yes. The two states are equivalent if the response for each possible input sequence is an identical output sequence. That is, for all the possible input sequences, if we apply them to two different states and the corresponding output sequence is also identical, then these two states can be considered to be equivalent state. Again, this definition can be recast to form that the two states are equivalent if the output produced for each input symbol is identical and the next states for each input symbol are the same or equivalent. That is, for each input, the output is identical and the next state is also identical. So let us see how this can be proved. If you look at the state diagram over here, just concentrate on the states 1, 0 and 1, 1. Okay, before going to this, there's a very interesting feature. If we look at this state diagram that I forgot to mention is that suppose your state is at 0, 0 and you put an input equal to 1. What will happen? The corresponding output will be 0 and it will move from 0 0 to 0 1 state. Now if input remains 1, then it will again move over to this with output still remaining 0. If you again put 1 0, so it will move over this. So output still remaining 0. And if you continue the input to be 1, what will happen? It will continue to stay at this state 1 0, with the output being actually equal to 0. So this will continue until you change the input to 0. As soon as so for 1 0 input, it moves over from 0 0 to 0 1. Again, for 1 input, output is 0, it moves over to 1 1. For 1 input, output is still 0, it moves over to 1 0, and it stays there as long as the input is kept 1. As soon as you change the input to 0, it will then revert back to 0 0 state, and only then it will produce an output 1. See, this sequence is very easily understood by just looking at the state diagram. That is the beauty of the state diagram. This pictorial representation makes this analysis very, very, very simple. তাই তো তোমাকে টেবিলটাকে ভাবতে গেলে অনেক ভাবতে হতো, but since you have a pictorial representation with this directed paths emanating from these different states, it's very easy to find out the transition, right? Now let us concentrate on the two states, like 1 0 and 1 1. Right? So let us see what happens if input is 0 and it is at 1 1 state. Then what will happen? It will produce an output equal to 1, and the transition will take place from 1 1 to 0 0. And if it is at state 0 0, then with an input 0, the output will be again 1, and the transition will take place from 1 0 to 0 0. See, so for input 0, the corresponding output are same, and the next states are identical for input 0. But this is not exclusive. There is another set of input that may happen, and that input is, say, input equal to 1, and say it is at state 1 1. So what will be the corresponding output? If it is at 1 1, if you give input equal to 1, the output will be 0, and what will be the next state? The 1 1 state will move over to 1 0 state. Now if it is at state 1 0, and if you give an input 1, what will be the output? 0. And what will be the next state? This 1 0 will continue to be at the state 1 0. So for input 1 also, the output of these two states are same, and the next state transition is also identical. So we can say 1 0 and 1 1 as equivalent states. All the possible input sequence 0 and 1 দুটোতে দেখেছি, এবং তাতে দেখেছি আউটপুট সেম, নেক্সট স্টেট ট্রানজিশনও সেম, 0 তেও যায় 1 এও যায়। So 1 0 and 1 1, they're basically same state. So what we can do, we can represent this circuit in an equivalent model, which will be like 0 0 0 1 followed by a state that is basically 1 0 and 1 1. So what are the transition? So this transitions will remain same, 1 0 0 0. So if it is at 0 1 and then one's input is applied, the output will be 0, and the next transition will be 1 0 or 1 1, which is equivalent to 1 0. And if it is at 1 0 1 1, if you apply an input 0, the output will be 1 and it will move to 0 0. And if you apply input 1, the output will be 0 and it will move to the state 1 0, irrespective what? Irrespective of the fact whether it is at 1 1 or 1 0, this will happen. Right? So this is how the equivalent first stage equivalent state diagram would look like. Now let us take a look at the states, this new states 0 1 and 1 0 1 1. Let us see what about these two states. If the input is at the state is at 0 0, right, the previous state, and if your input is equal to 1, what happens to the output? It becomes 0 and it moves to state 0 1, right? Now if it is a state 0 1, now your input is 0, it's at 0 1. So what will happen? The output will become 1. I have not shown over here. So this path is there. It is 0 1. Okay, this path. And what will be the next state? The 0 1 will change over to 0 0 for input equal to 0. What about if it is at 1 0 or 1 1, this equivalent state, and your input is 0, and what will be the output? Will be 1. And this 1 0 1 1, whatever it will then change over to 0 0. So this input equal to 0 condition is identical for 0 1 and this equivalent state 1 0 1 1. What about the other input? That is, which one is not necessary? I think I'll remove this. Next case for state 0 1. Here, sorry. Here, input equal to 1. It is at 0 1. So your output becomes 0 and 0 1 transits from 0 1 to either 1 0, not 1 0, sorry, transits to the state 1 1. See, 0 1, given input 1, output will be 0 and you will transit from. What about the present state is 1 0 1 1. Input is 1, so output will be 0. And this 1 0 1 1, if you put is 1, it will be 0. See this path, and it will remain there. So in this case also, see, for input equal to 1, the transition is from 0 1 to 1 1, and for input equal to, for both the cases. And we have seen for input equal to 0, the transition was identical. So you can say that this state 0 1 and this equivalent state 1 0 1 1, then again equivalent. So what you can do, you can cluster these two states together. So equivalent hoche. 1 0 1 1, we have already decided, find out that they are equivalent. And the transition from 0 1 to 1 0 1 1 and 1 0 1 1 to 0 0, they have also depicted that 0 1 and this cluster 1 0 1 1, they are also equivalent. So we can cluster this 1 0 1 1 with 0 1 and represent them as a single unit. So what will be the final equivalent state diagram or the reduced state diagram? Is somebody trying to join now? The reduced state diagram for this will be looking like this. We'll have a state 0, 0. Then we'll have a state 0, 1, 1, 0, 1, 1. And this will constitute an equivalent state, and the transition from 0, 0 to 0, 1 will be with the influence of input 1 with the corresponding output being 0, and this reverse transition will be under the influence of input 0 with a transition of output to 1. If it is at 0, 0, and if you give an input 0, it will remain 0 with output 0. And if it is at this state, and if you give an input 1, it will produce an output 0, and it will stay within this. So this, see, if you look clearly, this state diagram is being first reduced to this with 3 states instead of 4. Now we have reduced this to a 2-state diagram. Okay, so what you can do, you can clearly see, to develop this circuit we require 2 flip-flops. But since there are only 2 states, you can represent this as equivalent to state 0, and this equivalent to state 1, and this can be represented by using a single flip-flop. So you can reduce the overall number of flip-flops in the circuit. But one important thing is to be noted here: the reduction in the number of flip-flops doesn't mean the circuit will become simpler, because to accommodate this equivalence in state, what we have to do, we have to put some combinational logic gates in between, okay, as a feedback path to a particular flip-flop. So this reduction in number of states shall not always translate to a reduction in the design complexity. In some situations, it will become very, very complex, involving a lot more logic gates. The requirement for flip-flops will be reduced, but the logic gate requirement will be much more. But the advantage is that the transitions, the principal transitions, can be found out very easily. These are the principal transitions that can take place. Or the pictorial representation will be much, much concise. Since these are only 4 states, this reduction may not seem very, very helpful. But if there are, say, 16, 32, or for 64 states, then reduction of that to 8 states or 4 states will be very, very helpful, right? So in those cases, this reduction with the concept of equivalent state will be very helpful. The next thing that we should consider is the concept of a mixed model. How it can be called a mixed? Why it's called a mixed model? Mixed model means it will have the features of Mealy plus mood circuit representation in a single diagram, single state diagram. How? If you concentrate on the state 0, 0, right? Now, in this state, if the state is at 0, 0, if you give your input equal to 0, what is the corresponding output? 0. If you give input equal to 1, what is the corresponding output? Still 0. So for this state 0, 0, the output is independent of input. So this state 0, 0 basically follows mood model. কারণ দেখো তুমি state 0 0 আছে, তুমি 0 দাও, আউটপুটটা 0 হবে। It is, we're not concerned about state transition. We're only concerned about the corresponding output following a particular input. If you produce an input 0, the output will be 0. If you give an output input 1, the output still remains 0. So this is a particular mood model representation in the circuit. But the same is not true for all other states. How? See, for 0 1, for input 1, the output is 0. But for input 0, the output is 1. So it is not a mood model. The output is depending on the input. So it's a milli model. So for 1 1, if you give 0, the output is 1. If you give 1, output is 0. So it's again it's a milli model. For 1 0, for input 1, output 0. For input 0, output 1. So it's also a milli model. So only thing is that this 0 0 is a mood model, and rest are all milli models. So this state diagram can be termed as mixed model. Okay, or to be very precise, it's called a mixed output model. To be very precise, because some of the outputs are functions of the input, and some of the outputs are not functions of the input. The outputs corresponding to state 0 0 are independent of input, so that corresponds to a mood model. Whereas the outputs corresponding to the other 3 states 0 1 1 1 1 0, they are dependent on the input. So that's why it's called a milli model. So this is a mixed output model representation, right? So I shall stop here today. Okay. So do you have any questions, any queries regarding today's lecture? I guess there's no questions from your side. I request you to take a snapshot of this page, because this is not there in your tutorial sheet or the PDF. So take a snapshot of this. So take a snapshot of this. Okay. So I'll stop here today, since you're not having any queries, right? My question is, are you there? Is anybody there?
Yes, sir.
Yes, sir.
Okay. So we have understood what I have taught today.
Yes, sir.
Okay.
Yes, sir.
I will just provide you with a note. We just go through it. Okay. In case of any doubt, we will discuss in the next class, right?
Okay, sir.
Okay.